So far we have done control volume analysis with an understanding that the control volume is stationary, but the control volume can itself have a very arbitrary type of motion. To understand that how to address such an arbitrary type of motion, we will take the case now, the consideration of arbitrarily moving control volume. Remember that this is normally an advanced topic which may not be covered in depth in the undergraduate level, but this is a very important component. So we will prepare the mathematical foundations that are necessary to appreciate the consequences of this. So the first mathematical foundation that we will cover is derivative of a fixed vector in a rotating reference frame. So let us say that there is a vector A which is a fixed vector on a rotating disk. That means if you are sitting on the disk you will see it fixed, but if you are sitting outside you will see that it is changing its position, although it may not change its magnitude, but it will change its direction and therefore that will have a derivative. Our objective will be to calculate that derivative. So this vector after a time interval of t plus delta t will be there. So the change in the vector is this one, delta A. This is nothing but the triangle law of vector addition, by which you see the change as this delta A. So dA dt it will be limit So this is limit as delta t tends to 0 okay. So then we can write this delta A as the magnitude of this times the unit vector in this direction. So let us say that this is ER unit vector along R direction and this is E theta unit vector along theta direction. So because A is along ER, delta A is along E theta. Why? See, this angle delta theta is very small, so this is as good as 0. Sum total of the 3 angles of a triangle is 180 degree. So sum total of these two will be very close to 180 degree, this being close to 0. These two sides being equal, these are each roughly 90 degree. So delta A we can write now what is delta A? Delta A, so if you consider this angle to be roughly 90 degree, delta A by A is tan of delta theta, and because delta theta is small, tan of delta theta is as good as delta theta. So delta A will be A delta theta. So it will be limit as delta t tends to 0 A E theta into delta theta by delta t. By the definition, limit as delta t tends to 0, delta theta by delta t is omega, which is the angular speed. So this becomes A omega E theta. Okay. Now let us separately calculate what is omega cross A. This omega angular velocity vector is the omega scalar times the unit vector along the z axis, because the rotation is taking place in the r theta plane. So the rotation vector is the z axis. Cross A is A ER. So Ez is like the unit vector k and ER is like unit vector I. So it is k cross I. So it is like J. So this will be omega A, J in this case is E theta. So we can say that our conclusion of this entire exercise is dA dt is equal to omega cross A. Here we have considered a fixed vector in the rotating frame, but if the vector A itself is moving, then the total dA dt is the dA dt as you see from the reference frame plus this, which is due to the change in direction of the vector A. So we can summarily write so if we consider small xyz as the reference frame which is arbitrarily moving, and capital XYZ is a reference frame which is stationary. Then we can write okay. This is known as Chesel's theorem. For the case of momentum conservation, our point of interest is acceleration essentially, and acceleration means basically the double derivative of displacement. So the displacement has to be first worked out, and in that respect we start with an arbitrary point P here with a position vector r. So the second derivative of time with respect of r, or the second derivative of r with respect to time, that will give the absolute acceleration of the particle P. But we are not observing it from here, we are observing it from here. So we will express that in terms of the quantities observed from small xyz. To do that, we will make some constructions. We complete this vector triangle. So we can write that R so dr dt with respect to capital XYZ by Chesel's theorem, this will be or in simple notation we will call this as r dot with respect to small xyz. To get the acceleration, we need to differentiate it once more with respect to time. So derivative of this with respect to capital XYZ, what is that? That is derivative of this with respect to small xyz plus omega cross this, right. So d dt of which one? Just let me write this. Which one should be capital? this is capital S and this is capital, alright. This capital is with respect to small, this one, no, this is, see this Chesel's theorem, this with respect to capital XYZ is equal to this with respect to small xyz plus omega cross this, right, okay. So omega cross this, then the derivative of this one, that is the final thing. So plus okay. So then the only task that remains is a simplification of this. So this will be omega dot cross r plus omega cross r dot small xyz. So let us write this equation neatly somewhere at the top. So this 2 omega cross V xyz comes from one from here and another from here, and r dot is V. So now let us write it with little bit physical notation. What is this? This is nothing but the acceleration of the control volume, acceleration of small xyz, because r naught is the vector that connects the origin of the inner stationary frame to the origin of the moving frame. So its second derivative with respect to time is the acceleration of the control volume itself, linear acceleration. This is nothing but acceleration of the point P with respect to small xyz, and this is acceleration of point P with respect to capital XYZ. So what we can do is we can write one in terms of the other. We can write just this as the first term, actually this is this one and this is this one. This we call as A relative, just a name. Now let us say that we write the Reynolds transport theorem with respect to small xyz, which is a arbitrarily moving control volume. So in the Reynolds transport theorem you write capital N is equal to these two are essentially the same. This v relative is velocity with respect to small xyz. Now this you can write and by this it will be right, just this equation I have written one below the other. So this, now what is this? This is the resultant force acting on the system. Because this is control mass system, so we can apply the Newton's second law directly. So this becomes resultant force on the system. As the Reynolds transport theorem was derived in the limit as delta t tends to 0, so this will be resultant force on the control volume. So this term will be resultant force on the control volume minus this also you can evaluate on the control volume by noting that in the limit as delta t tends to 0, system and control volume they are all converging. So to get a summary, we can use the Reynolds transport theorem for an arbitrarily moving control volume for momentum conservation, but for a correction term where the force is replaced by force minus integral of dm into A relative. So this is an additional effective force which is like a pseudo force, that means a force which you can experience only if you are located on a arbitrarily accelerating reference frame, right. So this pseudo force is a combination of what? One is the acceleration, the linear acceleration of the control volume, so minus mass into acceleration, then minus omega cross r integrated over the mass. So this is called as centrifugal force. So if you are located on a rotating reference frame, then you will appear that or you will feel that there is a force which is trying to move you radially outwards. This is called as centrifugal force. This force is a pseudo force because this force you can experience only if you are sitting on the rotating reference frame. But if you are sitting on the inertial frame, you do not see that force, but you realize that in the form of an effective acceleration that is accelerating you towards the center, that is called as centripetal acceleration. So if you are observing from a inertial frame, the net effect is a centripetal acceleration, which is acceleration towards the center. If you are observing from a non-inertial or rotating reference frame, the net effect is a centrifugal force which is radially outwards, because one is expressed as an additional negative force, in the other the centripetal acceleration is expressed as a positive acceleration. So their effects are equivalent. Either you write minus mass into acceleration in the force, or in the right hand side you write it as mass times the centripetal acceleration, but you should not take the same effect twice. The next one, this is called as Euler force. So this is the force due to angular acceleration of the reference frame, and the final one is very interesting, it is called as the Coriolis force. So what is this? So if there is a rotating reference frame on which there is a point which is moving, then the translation relative to a rotating reference frame will make it experience a lateral force which is minus 2 omega cross the relative velocity. This is the force because of which, because of the rotation of the earth, the ocean currents which are moving relative to the earth will be deflected in certain directions. So Coriolis force is very important in fluid mechanics. The example that I gave is an example of atmospheric and oceanic science, where the Coriolis force is applied, and this is in the broad purview of geophysical fluid dynamics. So we now know that how to express the force balance in a moving reference frame. It is not just a simply moving reference frame, but a reference frame which is arbitrarily accelerating in terms of linear and angular motion. We will apply this to an example which is motion of a rocket. So let us say that there is a rocket which is represented by the schematic. This is the direction in which the rocket is moving, and this is the direction of gravity. So what is there in the rocket is that the rocket has its own basic structure, plus it is carrying some fuel. These fuels, when there is combustion, they will come out as the products of combustion with very high velocity, and that will give an upthrust, which is essentially a momentum flux which comes out of this, and that will take the rocket to a higher level. So the key here is that this velocity has to be so high that it can defeat gravity and also the drag force exerted by the air because of very high relative velocity, and still the rocket can move against gravity. Let us say that VE and AE, so this is the relative velocity of the product of combustion that is coming out of this exit with a exit area of AE. Our objective is to find out what is the velocity of the rocket as a function of time. So to do that, we will make a control volume like this. So we will apply this equation. See here the control volume is small xyz, which is the rocket itself, this is not rotating. So all the rotational terms will be gone, but only the correction term will be minus integral of dm into the acceleration of the control volume ACV. So what is the F? Let us consider the upward axis as the positive axis. So F is minus drag force minus gravity force. This is instantaneous because mass within the rocket is itself changing with time, minus acceleration of the control volume is dVr dt because you are measuring the velocity relative to small xyz. The relative velocity with respect to that is 0 inside the rocket except at the outflow boundary. So this term is 0 inside the rocket and this term, so what is this here? This is minus VE, it is a one dimensional problem, so the vector becomes a scalar with plus or minus. So this is minus VE and this V dot eta is positive because it is outflow. So minus rho AE into VE square. Okay. Keep one thing in mind, let us say you are not able to figure out whether it is plus or minus, somehow you have made a mistake. So this is where you apply your physical judgment. What is the physical judgment? See, the velocity of the rocket will be more and more higher and higher the speed at which the products of combustion come out. So these two must be of the same sign when they are put in two sides of the equation. So dVr dt should be increased with VE square and that is happening to be the case here. So doing dot product, cross product, whatever, these things are important but not at the expense of physics. Do not lose the sense of physics in your mind, and that sometimes can help your students to understand and synthesize the problem in a way that they can work out the problem quickly without going through always the cross product, dot product, these types of things. So then the final step is that now what is the mass of the rocket? So for that the mass balance has to be written. So this is 0, so this is 0, so this is m dot E into VE. M dot E is rho E into AE. Okay. So if you integrate it, then mr will be equal to m0 minus m dot E into VE into T, right. So this will be a function of time, this will be a function of time. Very often this is negligible as compared to gravity. So you are left with the following differential equation: dVr dt this one, right, yes, I have written one V extra, right. So m dot E into T, yes, where m dot E is rho E into V, A, so into V, nice. So this one, okay, so rho E A V into T, this one minus G, right. So now you can integrate this with respect to time, it will be logarithmic, and it's straightforward integration, I am not getting in going into that. What I will do is that we will spend a little bit of time, maybe 1 minute, to figure out that what is the role of different forces here. So role of the drag force is to bring it down, and the role of the gravity is to bring it down, the role of the momentum flux is to make it go up. That is why in junior classes it is called that the rocket goes up by either Newton's third law or the conservation of momentum. What it essentially means is that there is a momentum flux that comes out that gives a upthrust in the opposite direction, and that brings the rocket up. We have done most of the thing here, one conceptual anomaly needs to be resolved. While deriving the Reynolds transport theorem, for the system term we have considered a fixed mass, right. Now here for the system term we are considering a variable mass, right. This MR is not a, so I mean this anomaly comes from the fact that when you write dm into A, so essentially you are writing ddt of dmv, right. So this you are taking inside and attaching it here, but not giving due importance to this, right, but essentially this itself is a function of time in this particular case, right. So we can get rid of the situation again by freezing or snapping the phenomenon at a given instant of time when the system and control volume are merging. So instantaneously whatever is the mass at that instant, that is the mass within the control volume, as well as that is the mass of the control mass system that you can think of, and you can work with that instantaneous mass, assuming that in the limit as delta t tends to 0 your system and control volume they converge. So this is a subtle concept, and this is a contradiction. All of us learn through contradictions, and this is a very important contradiction. The contradiction comes from the fact that you have a variable mass, but still you are relating it to an equation which fundamentally relates a control mass system with control volume, and control mass is by definition a fixed system mass. So this is instantaneously treatable as a control mass, that is how you have to interpret it. Thank you very much. In the next lecture we will discuss about angular momentum.